In this section, we repeat what we did in section 9.2, but rather than for proportions, these are significant tests about means. So we assume the variable is quantitative instead of categorical. The data reduction employed randomization, we always do that. And this time the population distribution is approximately normal. And this is crucial if you have small n and h sub a. The alternative hypothesis is one-sided. So you notice here that the null hypothesis and the possible alternative hypotheses have a very similar form to what we had before. Instead of p equal p sub naught, it's mu equal mu sub naught. That's really the only change there in how it'll look. Our test statistic this time is using t-values. So to find t, we take x sub naught, the observed value, minus mu sub naught, the value we assume it to be, the null hypothesis, and we take s, which is the standard deviation of the sample, divided by the square root of n. So we're dividing the bottom by the sample error for the sampling distribution, and we find how many standard deviations away we are in terms of normal, but in terms of t. Remember, t has a thicker tail and actually gives us a better estimate. If we use z, we'd have some error in here. And using the t distribution gets rid of that. And we have to know the degrees of freedom, so you have to know n minus 1 is equal to the degrees of freedom when you look it up in the table. So when it's true for the null hypothesis, the t statistic is approximately the t distribution. And we're going to call the stat that we calculate the t statistic. So here they give you a picture of it. They're saying the possible observed one is, for the stat, is 5.54. And the p-value is the sum of the areas in the two shaded tails for the one they're showing you. So once again, the p-value summarizes the evidence, and we're going to use that to make a conclusion. So we have those possible alternative hypotheses. Either mu is not equal to mu naught, mu is bigger than mu naught, or mu is less than mu naught. So that time you're looking at the tails, the last two. And then again, we do the conclusion based on the p-value. We interpret what it says about the question that we started with before we did the experiment and the calculation. So here we're going to look at a study comparing psych therapies for teenage girls suffering from anorexia. But before that, think about this for a minute. Suppose I came in and I said that the average weight of people in the class was 125 pounds. And then we took a sample of people in the class, 5 or 6 people, and we found the average weight. Now, if their average weight was 250, we'd say, well, it sounds like the 120 was really too low. And if the average weight of those 5 people or 6 people we took the weight of averaged out to 80, we might say, well, it looks like that 120 was too high. That's really what we're doing. We're seeing how far away our sample statistic is from what we assume it to be. If it's really far away, we're going to say, well, the evidence seems to suggest that our initial hypothesis, the null hypothesis, is incorrect. So this time we're doing it for a variable where we're looking at the weight change in a girl who's undergone psychological therapy to help with anorexia. So if the girl gained weight, the weight change is positive. If she lost weight, it was negative. So we had 29 girls who received the therapeutic treatment, and the average change in weight, X bar, was 3 pounds, and the standard deviation for the sample was 7.32 pounds. And they give a table showing all that. Now you notice that n is less than 30. How can we make this into a significance test? And you should be doing this beforehand. So the null hypothesis, the one you want to disprove, it says that the therapy has no effect. The alternative hypothesis says it's effective. So no effect means the weight change is 0. If you want it to be effective, there actually is a positive weight gain, correct? If it's not effective at all, in terms of it's even worse if they undergo therapy, they would lose weight and it would be negative. Now, these girls were not picked at random from the population or from a huge population of anorexic girls. So it's not truly a random sample, but it might actually work pretty well, and then from there you go to later studies. And it's approximately normal because we have 29, which is close to 30. I think you were given that for this one anyway. So we're making an assumption if we aren't given that. And there are our null hypothesis and alternative hypothesis. The null hypothesis says there was no weight gain due to the therapy. The alternative hypothesis says there was a weight gain. It was something bigger than 0. So we form our t-statistic by taking the x bar that was observed and the sample minus what we think is mu sub naught, which is 0, divided by the sample standard deviation, which is 7.32, which itself is divided by n. So the bottom part is the standard error, the top part is the change between the observed value and what we suppose it to be, and we get 2.21. So we look at the p-value to the right of t equal 2.21, and we use a degree of freedom of 28. We find that it's 0.018. So this is saying that, well, if the treatment had no effect, this would only happen about roughly 2% of the time. So it looks like it actually did have some effect. Now that effect may have been small, but it had some effect. So it's pretty good. Usually our p-value, we want it to be 0.05 or less. This is certainly less than 0.05. 0.05, I should say, sorry. And they actually do a confidence interval here, using x bar, and adding and subtracting. We get this range from 0.2 pounds, not a lot, to 5.8 pounds, which is a pretty good amount. So somewhere in there we think mu is. We don't say mu is equal to x bar in the confidence interval. We say mu is somewhere in this range. 95 out of 100 times, but we can still be wrong. So our conclusion is, in a two-sided test, if it's less than that, that interval does not contain the h value, so we reject it. And the sampling distribution of x bar is approximately normal, even though the population distribution may not have been. Remember that? That's where you picked it. It's an unbiased estimator, and it's approximately normal. And the higher we get, the better. So we had 29, that's pretty good. 30, great. 100 is fantastic for our sample size, for that purpose at least. So when we have small samples, we can't do that, especially if we have something that's highly skewed or we have outliers. It actually messes up our assumptions about approximately normal. So what it does is it affects the sample mean if you have an outlier. So if we average a salary of less than our class, we come up with one number. If we added some billionaire to it and averaged it, it would really change the mean quite a bit, and that would make it misleading. If we took somebody who actually had no income and put them in there, they were living on subsidies from the government, so they officially had no income, that would be 0. That would also change the sample mean. So that's the effect of outliers. If you had a few like that, that actually skews it even more. And that finishes this section.